Hey folks, great to see you all. Really excited to be here. My name's Russell Kaplan, co-founder and president at Cognition. And today we wanted to talk about just building with agents and what we're seeing in real world enterprises, adopting AI for software engineering, what's working, what's not working, and sharing some details. Before we get into it, I guess, can you raise your hand if you've ever heard of Cognition or Devin or Windsurf before? Great, okay, basically everyone. So for those who haven't heard of us, we are an AI software engineering company, an agent lab. We started almost 2 years ago, originally as a research lab focused on long-term reasoning and planning. We're lucky to work with many of the largest, most sophisticated enterprises in the world, as well as thousands of companies globally. When we got started, it was really out of a love of software engineering and programming. Many of the folks on the founding team are competitive programmers by training. I joke that Scott is the CEO because he has the most gold medals on the team. He's the most in the history of the United States. And he's actually still the coach for the US national team on the side. So it's a bunch of people who really love to code. And we noticed in the sort of end of 2023, early 2024, that AI has made lots of progress in chat and real-time interfaces. But reasoning was really falling behind, and you couldn't really give real-world, long-term, end-to-end work to AI systems and have this work actually well. So we started Cognition originally as a reasoning lab, focused on long-term thinking, planning in the context of software engineering. And it's been a really exciting journey so far. We are now nearly 200 people with several offices around the world. We've raised about $700 million, most recently at a $10 billion valuation. And we're deployed at a lot of great companies, including some of the folks in this room. One thing we've seen is that the ability of AI to code well has been increasing significantly since the beginning of AI products in software engineering. And there's lots of different ways to measure this. This is just one example. This is the merge rate of Devin pull requests. So every time someone gives Devin, the AI software engineer that we make, a task to go do, that task will result in a pull request, and it will be automatically submitted and up for a human to review. And this rate at which these requests are getting merged is steadily increasing, and it's doubled to almost 70% over the last year. And these workloads are, these are not one-line fixes. These are kind of 4 to 8 hour, typically like junior engineering to mid-level engineering scope tasks on real-world production code bases. But what we've seen is that in the kind of broader ecosystem, most teams in industry are significantly behind using the full potential of AI for software engineering. And today we want to talk about why we think that is, what are the important ingredients to change that, and what are some examples of this already working really well at scale. To put this in perspective, I think you could really view the progress of AI tooling in software engineering over sort of 3 waves. And the first was really like the kind of Copilot tab completion style wave, where you're in your editor, you're writing some code, and you get a prediction of what code should come next. It's a very real-time synchronous experience for sort of line-by-line programming or function-by-function programming. And this already was an amazing product experience. GitHub Copilot really led the way in this, and it's been used by many, many folks all around the world for real productivity gains. The second wave has been full AI IDEs. So no longer just tab completion, but a completely sort of new development environment built for the ground up for leveraging AI at every turn, both for tab completion, but also for chat, for code-based understanding, for local synchronous agents working with you, for documentation, for all of the sort of ways you could get leverage from AI at every turn. The third wave, which is really the most recent, is the full AI software engineer. So this is more coworker than Copilot, something you delegate complete units of work to, maybe going directly from a ticket to a full finished pull request. And what we've seen is that across these different ways of working, these types of systems are already having meaningful, real impact at scale in the enterprise. As some examples from our customer base, one top 5 global bank measured a roughly 16x faster migration timeline for 40,000 legacy ETL framework files going to Java. Another example is test coverage, automation, and improvement. Top 3 global retailer measuring at least 90% of system coverage, system testing coverage after using AI to improve both unit and end-to-end integration tests written automatically by AI coding agents. A third example is documentation and indexing and code-based understanding. One of the largest banks in the world has more than 300,000 repositories documented automatically by Cognition. And this includes very legacy systems as well as very modern systems. And we're also seeing this in project velocity. So a Fortune 5 healthcare company that's getting a multi-X improvement in product velocity as measured from the beginning of when you start up the project to when it's going to ship, how you would have done it the old way, how you are doing it the new way. And so some of these companies are doing really well, basically deploying these systems and getting real value of them at scale. And we've worked with many such companies now, more than 1,000 enterprises around the world, and we've noticed a few patterns that are common among the folks who are the most successful at deploying and using AI. So we're going to talk about what these patterns are from the product and rollout perspective, and what they are from the change manager perspective as well. So first, the deployment patterns. The first is a recognition that different forms of AI for software engineering have different fundamental technical trade-offs. And so multiple modes of using AI are actually quite important, both the real-time synchronous assistant type workflow and also the asynchronous, more autonomous delegation type workflow. The second is that understanding the existing code and context inside a company is really critical to getting true real-world value. It's actually relatively straightforward at this point to build an AI system that can kind of prototype a new website or product from scratch. But to work within the context of an existing business that has its own requirements, proprietary frameworks, historical decisions that have lots of context that maybe no one person even has, and maybe regulatory or process requirements that have to get followed for code to be successful, it's a lot more complicated. And we've learned a lot about how to do that well and not well, and why that's really important for driving real-world results. The third is how do you start to use these AI tools to help improve velocity across the entire software development lifecycle? Writing code is one part of that, but it's only one part of that. And the next generation of productivity gains, to go from the 10, 20% to the multi-X, all involve automating entire swaths of the SDLC for specific workloads, not just the writing code. So a little bit more on this first point of multiple modes of working with AI software engineering tooling. We're finding that it's relatively easier to adopt synchronous, real-time AI assistance. Developers are already very comfortable in their IDE. And this paradigm of working in flow state, writing code, has been the way we write code for a long time, right? From Vim to modern IDEs to now agentic IDEs. You're in flow state in your editor, writing code, just now with leverage and speed up from AI systems. At Cognition, we make Windsurf, the agentic IDE that's designed to keep engineers in flow state as they're programming. And there's a fundamentally one-to-one relationship between each engineer and their real-time AI assistants. So immediate speed-ups, very useful for challenging creative work where you have to be working hand-in-hand with AI to deliver outcomes. Increasingly, a lot of software engineering has become addressable by a completely different form factor, which is the asynchronous, autonomous delegation style model. You have an AI engineer that's actually doing the full work end-to-end, from the details of the scoping to the implementation, to the testing, to the review, to the complete proposal of a pull request. And this has different technical trade-offs. So it's asynchronous instead of synchronous. It's going to take longer. But you can kick off many of these in parallel. And because it's asynchronous, you can tolerate much longer latency in exchange for higher degrees of correctness and completeness. And there's certain workloads that are extremely appealing for this type of software engineering automation. There are others where it's frankly too hard, and these systems are not yet good enough to do this reliably. Our heuristic that we found with Devin is that tasks that are roughly half day to 1 day's worth of work for a junior to mid-level engineer are about the right level of difficulty to delegate to any one Devin session. And for things that are more complicated, the human engineer is responsible for really breaking up that project into discrete components, and then you can delegate it to an entire team of AI agents. And in this way, the role of being an individual software engineer is changing a little bit to becoming kind of like a tech lead manager, where you're still writing some code yourself, but you're also increasingly delegating work to your team of async AI agents. And that's a fundamentally different workflow for a lot of folks. And it means that to roll this out successfully, there's a kind of a learning curve and an organizational change element that's really important as well. So how are we actually building towards this? With Windsurf, we're very, very focused on speed, keeping people in flow state. One of the first observations we found is that modern models make tough trade-offs between intelligence and speed. You can use frontier models, relatively slow tokens per second rate, and you're kind of waiting for a response from your chat or from code suggestions. And those few seconds really add up. They can interrupt your flow state. They can get you distracted. It's sort of the modern day equivalent of I'm waiting for my code to compile. On the other hand, historically, very, very fast models have had to make severe intelligence trade-offs to make them run quickly. We've done a lot of work building in-house RL models at Cognition to try to balance the best of both worlds. And we've recently released a new model family called SWE 1.5, which is achieving roughly frontier class performance on the sort of state-of-the-art industry benchmark for agentic coding, which is called SWE Bench Pro. So you can see in this evaluation, the x-axis here is the score on this benchmark on a standardized harness. And it's a little bit behind Sonnet 4.5. It's a little bit ahead of GPT, of the sort of frontier OpenAI model series. So it's not outperforming, but it's not underperforming on quality. On the other hand, on speed, it's in order of magnitude faster. So this is served at roughly 950 tokens per second, about 10 times faster than kind of other alternatives. And the way we made that possible was by building a lot of infrastructure and modeling in-house and partnering with Cerebras, the maker of wafer-scale chips, which collectively allow us to serve these models extremely quickly. And because of that, we get an end-to-end product experience where you can get results nearly as fast as you can think them. And we found that this is the key for staying in flow state as you're using AI tools yourself to create code. On the other end of the spectrum, you have the asynchronous delegation workflow. And so what's the best practice for making that really work inside a company? I'll talk through an example of a migration project, because this is one type of workload, migrations, modernizations, refactors, that are especially well suited to the Devin form factor. Typically, a large migration project first has to be architected by a senior engineer from the existing team who has context on everything going on in the organization and can make the right technical trade-offs of what's the desired end state we're trying to get to, and then also what's our incremental path there. That part of the process is not going away right now. We need humans to architect the desired end states of these migrations. But once you've done that architecting work, and you've kind of broken up how should this get done, you end up with lots of individual pieces. Maybe there are tickets in an Epic and Jira. Maybe there are specific ETL pipelines in a broader overall ecosystem. Maybe there are files or libraries in a monolithic repository where you have to do a major version upgrade to a modern version. Once you have those individual pieces, that's where you can start to really get the benefit of delegation to autonomous AI software agents. And so the workflow we found works best with Devin is after these pieces are broken up, you can delegate one piece to Devin, and Devin will work on the specific execution and implementation of that narrow change. And because it's broken up, that change is actually digestible and doable entirely end-to-end. Again, not just the writing of the code, but any further gathering of specific requirements that need to be accounted for, the writing and the planning of the code, and then the testing of the code. We found that since day one, when we launched Devin, every session runs in an isolated virtual machine, which in addition to having a code editor, also has a command line, it has a web browser, it has a full replica of the human development environment of the companies we work with. And because of that, after the code is written, the code can be tested, whether it's using existing tests that already exist inside the organization or having Devin write new tests to check its own work. Even if there are no tests, we found Devin can do pixel-level interaction on these systems so that you end up understanding, does this new website actually work when you click with it? Does this new desktop app actually work? And the result of that might be, hey, it didn't work on the first try. But that's OK, because this is an asynchronous form factor. So Devin can notice that and then fix its code, test itself again, fix its code, test itself again, until it gets to a state where it's very confident that the change is correct. Only when you're at that point is that change served up as a ready-to-review pull request for the human software engineer. And this can be parallelized across many components of the overall larger project in parallel. So this is the workflow that we're seeing for really deploying asynchronous autonomous software engineering agents at scale in a way that drives really measurable impact. If you imagine the day in the life of a software engineer who's fully embraced this modern suite of AI tooling, you might start out in the morning, the beginning of your day, planning out the work that needs to get done, delegating some tasks to your asynchronous agents, scoping some things in more detail so that they're sufficiently broken up, and firing off a lot of these things in parallel. Once those things are working, then you can sit down and actually start coding yourself in Windsurf or whatever tool you choose to have that flow state quick interaction with systems, especially for the more complicated, complex projects or projects that aren't really scoped, like complex greenfield development, where you're kind of building, you're discovering and you're building as you go. But critically, in this future mode of working, if you don't also have those asynchronous agents working in the background, you're not being very efficient with your time, because you could have also at the same time been delegating this work to others. It actually reminds me of my time previously where I was at Tesla on the autopilot team as a kind of computer vision scientist working on training neural networks for the self-driving system. And we had a rule of thumb internally that you can never go to bed with the GPUs idling, because you're wasting tremendous amounts of compute where the models could be working while you're sleeping. And I think what we're going to see in software engineering is kind of the same type of concept applied to working with asynchronous agents as well. The agent should be working while you are working too. And then it's time to check that work. Maybe after your lunch break, you look at the PRs ready to review, you leave some feedback, some are ready to merge, and then you can go back to your own coding, your own approvals, your own merging, and then the delegation again. This is the workflow of the most productive software engineers that we see in the organizations we work with, the mix of synchronous and asynchronous AI collaboration. One important lesson is that you have to really pick a side, synchronous or asynchronous, for any given workflow. And the worst experience is what we call the semi-async valley of death. It's those tasks that maybe take a few minutes, 1 minute, 2 minutes. It's enough time that you can't stay in flow state anymore. But it's not so much time that you're getting the full benefits of independent autonomy. It's OK to make things run for a very long time if by the time those changes come back, we're confident that they're likely to be correct. It's also OK to work closely hand in hand with AI systems yourself. The semi-async valley of death is what you need to avoid. And we've tried to build our product suite really embracing that, making different technical trade-offs for the different surfaces that we work with. The second pattern is that it's really important for agents to understand the existing code. This is, I think, the single biggest rate limiter on overall software engineering productivity, certainly for AI. I would argue probably for humans as well. This is one of the central challenges of scaling engineering velocity as the organization gets larger. No one person has all the context of what's going on. There are decisions that are made. There's historical details that are unclear. And a huge amount of time is spent gathering that context, grokking new systems, onboarding and ramping as a new engineer to a new part of the code base. And the same is true of AI. In AI, the issue is sufficiently exacerbated because models have limited context windows. And so if you're just working with an LLM as opposed to an agent, you'll run into this issue extremely quickly. Even most agents today very clearly struggle with working on larger, more complex systems, brownfield development, because of this fundamental lack of understanding, this lack of context. And we recognize that this was a central challenge to building agents that provide useful real-world work. And so earlier in 2025, we released a product called DeepWiki, which is a indexing and understanding of the macro scale context of your code base. This product surface is deployed at very, very large scale. For example, tens to hundreds of millions of lines of code. And these are repositories that could not be thrown into an LLM and used as context. We built this product experience originally entirely as an internal tool for Devin, so that Devin could have macro context on the code base it was working on as it was working. And we found that this tool was so useful for improving Devin and later Windsurf's performance that the human engineers on our team got jealous and said, we want to use this too. And we eventually decided, let's put a front end around it and make it available. And that's what became DeepWiki. And today, DeepWiki is available globally, free for all open source repos. You can change the GitHub URL of any repo to deepwiki.com instead of github.com and try it yourself. And it's also available for all the private code bases we work with across our customers. And I want to show you an example of what this looks like in practice. So here, I have a video of pulling up a very fun repo with lots of tricky context, the original Apollo 11 source code. So this is Apollo 11 assembly code that was written many years ago for the Apollo missions. And DeepWiki has gone and indexed this code and provided what's essentially a living, breathing Confluence page for this repo, where modules, architecture diagrams, macro context is all documented automatically. And we look at the code, not just the comments, because we found that the comments often drift from the code and are an unreliable source of truth in a large-scale organization. You can look into specific modules, get more detail, see the data flow, the interface contracts, and really go into a lot of detail. But sometimes you actually want to ask questions about the code base itself. And so we built that experience as well. Here, we're asking, where is the liftoff sequence for the Apollo mission actually implemented? And DeepWiki has gone through the code. It's found the specific key component that's most relevant. It's the P11 component. And it walks through how liftoff detection works line by line with the relevant assembly on the side as well. So you can validate the work of the AI, again, in this synchronous flow state experience. And here, you can see in even more detail what we call a code map. Code map is a human interpretable representation of what would otherwise be considered very complex control flow in code to follow along. So you can see on the left, we have a prose summary of the overall liftoff sequence, and then this indented, nested, kind of like pseudocode documentation for how the different components of this process work. On the right, you see the assembly, and these are mapped together. This code map experience, it lets engineers get much better detailed understanding of how these tools fit together. And this is live for all engineers in Windsurf today. You can use this interface to really understand whether it's a legacy system, a modern system, or a complex interconnected set of code bases, how these control flows fit together at different levels of resolution. Ultimately, scaling code base understanding is what affects agent productivity, but it also affects human productivity. We found that when folks are planning new software engineering projects, a huge amount of the time spent in the planning process is gathering this context. And our customers who have deployed this at scale have found that this capability is a very meaningful contributor to increased planning velocity. This is an example from IDEs, which we'll talk more about later. After rolling out documentation through DeepWiki to their existing repositories, they measured on average it would take literally 10 times as fast to plan the infrastructure architectural work for new projects. Rather than an engineer going off doing research, writing some Google Docs, scoping out here's all the things we need to do, it starts with an interactive DeepWiki sessions where the architecture diagrams are already there. They're validated by the engineer by looking at the source code and double checking. And the task is scoped and broken down through this search and natural language interface. What's the third pattern? The third pattern, arguably the most important, is that the productivity gains of the future are going to come from usage of AI coding across the entire software development lifecycle. It's no longer enough to just help with writing code. There's lots of different estimates on this. Microsoft and software.com have both estimated around 20% or less of human software engineering time in an enterprise is spent actually writing code. The rest is everything else. Understanding the existing code, planning what code we should write, collaborating with colleagues to make sure that those specs are accurate, writing the code, but then reviewing the code, testing the code, running QA through the code, fixing things that are found, repeating this process until a change is actually ready to ship. And if you think about how we've designed the SDLC, most of it has been designed assuming that the code writing part is the scarce resource. This is why we do planning. This is why we do project management the way we do it. It's that we couldn't waste engineers' time writing code that's not useful because that's such an expensive constrained resource. But what we're finding is that when you have this abundance of code writing happening from AI, everything else becomes much more of a bottleneck, much more of a bottleneck. And so to get the next level of productivity gains, you have to figure out how do we optimize the end-to-end system, not just one component of the system. As an example of each step here, on the code writing side, one of our customers, Nubank, they had a problem to migrate an 8-year-old multi-million line ETL monolith. This bank had grown very quickly. They needed help decomposing their monolithic ETL repository into separate modules so that each line of business could have independent control of their work without breaking changes for other lines of business. This was originally scoped to be an 18-month engineering effort, requiring some repetitive refactoring work distributed across more than 1,000 engineers. Ultimately, this type of workload fits extremely well in the async delegation paradigm we talked about previously. And they were able to do this project with 1/8 the human time at a 20x cost saving by delegating the work to Devin. The human work doesn't go away. You still have to scope out what's the desired end state of the changes. They should still be reviewed by a human before they're approved. But if you amortize the human time spent taken to review each change, and then for some fraction of the time, maybe making modifications or edits, on average, this was around 1/8 of the time it took to do it the manual way. And so the larger the migration that refactor the project, the bigger these gains can be in absolute terms. Once you've written the code, you need to review the code. And AI is also able to help with code review. Now, what we found is that increasingly as a paradigm, organizations are asking AI to take the first pass at reviewing the code that's written for correctness, conformance with organizational best practices, potential security vulnerabilities, and other issues. And only then does it make sense to spend the more precious human time looking at things on top. This can all be configured via API. This is an example of a pull request that was reviewed by Devin, where a SQL injection vulnerability was discovered automatically. You can configure Devin, you can configure any asynchronous agent experience to work well within the existing SDLC at the review layer too. But let's be real, there are some dedicated tools for things like static analysis of security tools. We don't have to throw AI at everything. In fact, when there's a deterministic way to do something, we strongly recommend do it the deterministic way instead. Only when that doesn't work should you use AI at all. But what we found is that the deterministic way plus AI leverage and automation is often the best possible solution. For example, many leading static analysis tools like SonarQube, Fortify, Veracode, Sneak, they produce huge volumes of findings that at enterprise scale can add up to lots of engineering toil to triage and remediate. Once these existing static analysis tools are connected to autonomous asynchronous AI agents, you get this multiplicative speedup where engineers only have to look at the alerts that have already been triaged by AI. And we find that organizations that adopt this are able to resolve 70% of static analysis tool security scan issues automatically with Devin. And we'll talk about more details of how that was achieved. There's also the test writing. Many of us know tests are important, but as individual engineers aren't super excited to write them ourselves, at least speaking in my own experience. But we're finding that agents are both transformative for helping improve test coverage and also really benefit from having better test coverage in an organization. If I were to describe one of the underlying best practices for working with AI inside your code base productively, it's making sure the feedback loops are tight. So how do we know that when this AI-generated change is created, it's actually going to work? And one of the best ways to do that is with test coverage, unit tests, end-to-end integration tests, and things in the middle as well. What we found is that if you have systematically under kind of lower test coverage in sections or large swaths of your code repositories than you want, you can do one-time pushes to go improve test coverage and make sure you're really monitoring the desired behavior of the existing system. And then once you have that in place, it unlocks further velocity gains from AI on every other use case on top. It's important that we're not just talking about the product capabilities that are needed to be successful, but also what's actually needed from the enterprise to roll these out in a productive way. And we have seen many of these rollouts with varying levels of velocity and success. And I just want to share a few best practices that we've seen for asynchronous agents in particular, but coding agents in general. The first is that this new generation of tools represent more of a workflow transformation than a new type of developer tool. It's coworker, not copilot. And so because of that, this is a big workflow change. It's also a new skill for engineers to learn inside an organization. We've actually found that people who are already engineering managers are sometimes the most productive contributors with this next generation of tools because they're already good at delegating. And so this is something that everyone is going to benefit from at some point in the future, being able to work as an individual contributor yourself, but also delegate productively to AI. And having internal teams that sort of lead the charge on this front become a center of excellence for the overall organization is really, really helpful to making sure that others can kind of learn from these best practices. And the most effective rollouts, they tend to combine the top-down mandate with the bottoms-up buy-in. Especially at large enterprise scale, you will have a wide range of engineering buy-in, from people chomping at the bit to use the latest and greatest AI tools to people who say, I have done coding the way I've done it for 30 years, and I am not changing. And we found that both approaches are going to be present and are going to be important for the future of productivity inside the enterprise. But the way to move the needle forward is to just celebrate the wins and make sure that there are folks who are getting success, that's highlighted, that's emphasized, and other people can learn from that. We've seen even the most grizzled skeptics discover a use case that they thought was impossible with AI and completely turn around and become an evangelist. But it requires this sort of social cohesion and organizational buy-in. Tactically, we've seen everything from people adding line items in the performance review rubric about AI utilization to doing specific all-hands or highlights of the best uses of AI that are discovered inside the team. The second is that the setup and the integration is actually really tricky, and it's also critical. Agents are going to be onboarded more like human engineers than like dev tools over time. Again, the best gains come from the entire software development lifecycle automation, not just one piece. And to do that actually well, you need access to the same tools and systems that a human engineer would use to do their work. So every Devin session, it's configured in a virtual machine that has an identical development environment to the human engineer's virtual machine. But if Devin doesn't have access to the same tools the human engineer would use to check their work, then the productivity gains are going to be capped. And a particular pitfall to avoid is the partial access rollout trap, where you've approved an exciting new tool, you're ready to roll it out, but you've only done it for the source code. And actually, for engineers to be productive in your systems, they also need to run the internal test suite. They need to run some internal tools. If you don't have those as well, you're leaving significant amounts of autonomy on the table. Imagine coding yourself without being able to run or test your code. It would be very hard. So this is a critical thing to get right. The second is that how you actually instruct these AI agents, it's a skill. It's not something that everyone inherently picks up, kind of like how you delegate tasks to coworkers or to reports on your team. We've seen prompts that are one line and extremely vague to build an entire end-to-end system from scratch that have very low probability of success. And we started to build in coaching and tooling in our own systems to help people learn how to work better with AI systems, and in some cases, automate the prompt creation process entirely. If you are going from a Jira ticket, which is often underscoped, we found that rather than just copy and pasting that Jira ticket into an agentic AI system like Devin, that if you assign that ticket to Devin, we will first do a detailed scoping deep dive, where Devin will research every aspect of your code base, understand what's all the relevant context for this particular ambiguous ticket, and then it will construct a prompt for itself. It's much more detailed. It says, these are the best practices. Here's exactly what we need to do. Here's how you can test your own work. And this type of meta-prompting is becoming increasingly popular. The next is that training, because of this complexity, the gains to training are actually really high. So if you imagine, we all know that some engineers have dramatically higher impact on the organization than other engineers. We think that that gap is going to actually widen with AI. Everyone's baseline moves up, but the best performers can become even more leveraged than before. And as an extreme example, you can imagine really productive individual engineers in your organization almost becoming like CTOs of an entire army of AI agents. That's the direction that software engineering is going. And so getting folks helping folks reach the closer to the ceiling of productivity gains can have like a multiplicative benefit. And there should be time for people to actually play and learn with these tools and knowledge sharing best practices the same way that we help each other learn coding. The second is, and the last, and this is very important, is like how do we actually measure this stuff? So metrics and measurement is one of the most talked about parts of AI software engineering. It's quite challenging for a lot of folks, and there's many different approaches for how to do this. On one end of the spectrum, you can have really granular input metrics, probably the worst one being number of lines of code written by AI. On the other end of the spectrum, you have complete end-to-end business outcomes. Great, we have saved X many billions of dollars or made X many billions of dollars from AI progress, and we've shipped at this much higher velocity. The way we think about it is that it makes sense to take metrics at multiple levels of abstraction, but over time, the higher impact metrics are closer to the end-to-end outcome-based metrics. That's really what matters. And so when we're seeing successful AI software engineering agent rollouts in large enterprises, most often this is measured on specific project timelines, shrinking dramatically, and requiring much fewer engineering resources. And the enterprises we work with almost always reinvest those engineering resources into more projects because the demand for code is sort of insatiable. And so people are shipping more and more and more. Migrations that maybe wouldn't have gotten done because they were infeasible before are now happening, and they're happening quickly. So the ideal is measure the wall clock time of large-scale projects. If it was going to take 2 years, now it's going to take 6 months. It was going to take 1,000 engineers, now it takes 100. That's the sort of the gold standard. One below that is how much human time you're actually saving on a per unit of work basis. This is another huge benefit of applying AI software engineering for the entire SDLC. If you take a Jira ticket and you assign it to an agent, and that agent solves it end-to-end, you now know how many story points were done autonomously by AI. And you have some accountability metric of that would have taken this much human engineering time, and that's worth this much to me. And the ROI is very easy to do. Absent that, you look at the velocity of teams. What's the merge PR rate? Are the number of merge PRs going up? Are we able to get more, to have more smaller teams outputting the same amount per team? This is how you actually capture the productivity gains of AI in a way that's deployable and parallelizable, as opposed to kind of survey-based and anecdotal. I wanted to talk about what this looks like end-to-end in the real world at large enterprise scale. And the customer I'm excited to share the details about how they did this successfully is Itaú. Itaú is the largest bank in Latin America. They're at global financial scale and very high complexity. They have $500 billion in assets, over 70 million customers. They operate across 18 countries, and they have one of the largest engineering organizations in all of Latin America, over 17,000 people working in technology. First, I want to talk about their results, and then we'll talk about how they achieve them specifically. Itaú has indexed more than 300,000 lines of code documented automatically with Devin. More than 75% of teams, spanning 17,000 engineers, are using Devin in production. 70% of all security vulnerabilities flagged by static code analysis tools are auto-remediated by Devin today. They measure, on average, 5 to 6x faster modernization and migration end-to-end wall clock time for projects. And they've 2x their test coverage from less than 50% to around 90% on key critical systems with Devin. So these are some of the results deploying this at scale. Itaú approached evaluating agents kind of like working with a new person on the team. Eventually, you're going to start with smaller tasks, build trust, learn how to work with that person, and then grow over time. One squad at Itaú used Devin for everything possible that they could, and they ended up delivering 2 releases in 3 months, which was double what they had originally planned. And on measurements of code quality and developer satisfaction, they saw significant performance gains using Devin. In terms of how this helped over time, just like when you're onboarding a new human engineer, when you onboard a new AI engineer, day one, they might know a lot about coding. Devin might know a lot about coding, but it's not going to know anything about you. This is a benefit of rolling out these systems early with compounding knowledge. Under the hood, every day you work with Devin, every interaction you have, it gets smarter, better, faster over time. It learns the specific organizational context that matters to you. And that makes future PRs more likely to be successful, more likely to merge, more likely to be relevant. This code-based understanding is, again, the key starting point of how these systems work. Where Itaú found this in particularly helpful was architecture documentation. This led to 10x faster planning. Again, many of these large-scale real-world systems are written by people who are no longer at the company with inadequate documentation. It takes huge amounts of time gathering data and information. One of the product managers for Itaú, named Stefano, he said that developers at Itaú have been excited by how far Devin can go. We've seen it handle problems we initially thought were too complex, especially for teams working across massive code bases where most other products struggle to absorb that amount of context. And I'll say one interesting side note is that product managers are some of the biggest beneficiaries of this new wave of tools. Because because product managers are often dependent on engineers to get their questions answered. But now, just like Devin is the first-line triage for static analysis security vulnerabilities, Devin can also be the first-line answer triage for questions from engineering-adjacent functions. Like, why ask the engineer when you could first ask Devin, get an instant answer that's grounded in the code, and that's been a killer use case for product managers. In terms of writing code, one of my favorite use cases that ITO deployed Devin at is what's called the CNPJ compliance project. So Brazil has, like the US, taxpayer numbers for companies. Unlike the US, Brazil's numbers for taxpayer numbers for companies used to be numbers, and a new regulation was passed, said they are now going to be alphanumeric. This is basically the Y2K catastrophe of Brazil. Every enterprise in all of Brazil is scrambling to become compliant with this new thing, and this is affecting really large-scale production systems that have been around for decades, including significant COBOL infrastructure at ITO that's mission critical to kind of maintain performance and compliance. Devin was able to do end-to-end migration for CNPJ compliance across all repos at ITO that were tested. One example was a SQL Server migration that covered 800 database objects that leveraged stored procedures and kind of legacy practices, and they were able to get this to compliance and completion with modern CNPJ regulation over 5x faster than was budgeted. Again, large-scale projects that you can break up into simple work. This is the recipe. And ultimately, what we're seeing is that CIOs are expected to get more done, and AI leverage is the best way to do it. The CTO of ITO said that speed is the ultimate competitive advantage. AI is the critical enabler that allows us to dramatically accelerate the ability to respond to customer needs, and this is a key part of their strategy and their success. With that, thanks so much for joining, and happy to answer questions from anyone in the audience. Thank you.